We're now going to go back and look at circular motion that is non-uniform. Now, the word non-uniform is nothing to make a big deal about. Non-uniform for us simply means that the object will be speeding up or slowing down. And now, if the object is going in a circle and speeding up or slowing down, then there definitely is this tangential acceleration. So that's my A tan here. So if the object is moving in a circle, and the velocity, of course, at any point in time is tangent, if the tangential acceleration goes with the velocity tangent, meaning within the same direction, then that object's speeding up. If A tan were to go tangential but backwards against that V tan, then the object is slowing down. So at any rate, red was A tan. So A tan always is the acceleration we associate with the object as it speeds up or slows down. A radial is only one thing ever. A radial is V squared on R always, and it is radially inward always. So, well, how do we go about problem solving a non-uniform or a circular motion problem where the object is speeding up or slowing down? The first thing that we need to do is analyze the tangential acceleration first. So A tan first, and I'll explain why A tan first. And when I say analyze, you're asking yourself, is it speeding up or slowing down? Of course, if the answer is no, then we're back to uniform circular motion. V is constant. In this case, the total acceleration equals A radial only, because A tangent in that case would be 0, right? If A tan is 0, you only have A total equals A radial. And we go back to our uniform circular motion, V squared on R, radially inward. Now, if the answer is yes, which it will be for our non-circular motion problems, then we need to determine, as I said above, whether A tan is in the direction of the tangential velocity or whether A tan is opposite the tangential velocity, to see whether it is speeding up or slowing down. So please get this into your notes. Once we have A tan, we are going to use the constant acceleration equations, and this is key. The technique you are going to use to problem solve is going to pretend that you actually take a pair of scissors and cut the circle and bend it into a straight line and use the constant acceleration equations to get a V final. V final is going to be what we really need. We need V final from these acceleration equations, where our x now becomes our position on the arc length, and when we do our example problem in a moment, you'll see that. The V final, because the V final is what we plug into V squared on R to get our A radial expression. So now we will do a vector addition tip to tail to get A total in terms of A tangential and A radial. So I have an example on the next page. I would like you to pause the video here. I'd like you to take a look at it. I'd like you to try to do it yourself, and then unpause the video and we'll talk about it together. So pause now. Okay, we're back. Hopefully you've looked at the example problem, and let's see the solution. Well, we're told that the particle moves in a clockwise, right? So it's moving along our circular trajectory clockwise from position A to position B. The radius, you're told, is 1 meter. And it starts at time t equals 0 at A and is speeding up. Look, it's speeding up at a constant rate of 1.6 meters per second squared. Voila, they gave us A tan. They're asking, how long does it take to travel halfway around the circle? Well, you take the scissors, cut the circle, bend it into a straight line, A to B, use my constant acceleration equations. Halfway around the circle is pi r. R is 1 meter, so just pi for x final. Started at position 0. Started from rest. A tan is the 1.6. We have our time that it took to go from A to B. And now everything begins to fall into place. We use that time to get v final. The direction of the velocity, I hope everyone got that right. That is always tangential, so that point B, the velocity is here, tangential, so it's going to be in the negative y-hat direction for this picture, but always tangential. The centripetal acceleration, v squared on r, we are going to use our v from part B in here to get our radial acceleration. They gave us, right? They gave us our tangential acceleration. And look, we can calculate the total acceleration at part B by doing the tip to tail vector addition, right? A tan plus A radial, or A radial plus A tan, you get the same answer, gives us our A total. Pythagorean theorem to get the magnitude of the total acceleration, and inverse tan to get the angle theta that we've specified in our drawing. So I think everything we have done has led us to the place where we can now solve these non-uniform speeding up and slowing down circular motion problems once we understand kind of the procedure to follow, analyzing A tan and cutting the circle as such. So you'll have some to work on your own. Let me erase my ink here so you have a clean page to look at. Pause it if you wish. And we will move on.